All right, Chapter 10, Section 4, Proofs with Perpendicular Lines. This is the first section in Chapter 10 where we're really going to start to focus on perpendicularity. And the main thing to understand here is that when it comes to two lines being parallel, most of us associate that with the lines will never intersect. We amended that in Section 1 by saying that not only are they never going to intersect, but more specifically, they never intersect on the same plane. That just kind of limits it so that if, for instance, I were to draw two lines on this graph paper, that would be the same plane, the plane being the graph paper. And they would be parallel because they would never intersect. Maybe they had the same slope. Okay, those two lines would be parallel. Now, perpendicular lines will intersect, but more specifically, they're going to intersect in a very special way. They're going to make a 90-degree angle. Now, there's something very important to associate with that. Not only will they make a 90-degree angle, but many of you have heard this phrase before. The shortest distance between any 2 points is a straight line. And that's still true. So for instance, in this diagram, if I were to connect A and P together, I could do it in lots of different ways. I could kind of like do a little windy path to get from one to the other. But if I want to do it in the shortest possible way, I would just do a straight line. Okay, the shortest distance between any 2 points is a straight line. But this definition is how we're going to amend it, because in rare instances do we connect 2 points together. What's actually more common is I have a point connected to a line or a segment, a surface of some sort. So for instance, in this scenario, maybe this is based on locations. Maybe point P is us here in Big Bear. Maybe your location at your house or at your desk in my classroom, wherever it might be, but maybe that's your pinpointed location. And maybe you're trying to find the shortest distance to some finish line, some border, whatever that might be. Maybe you're trying to get to the beach and say A, B, and C here are different cities along that beach, right? You're trying to get to the Pacific Ocean. So if you're trying to say like, all right, from Big Bear to say Long Beach or Huntington Beach or San Diego, okay? Now, there are lots of ways I can connect straight lines, straight segments from Big Bear to this beach, but some are going to be shorter than others. I could do a straight line all the way up to Northern California and get to the coast, and that would be the shortest distance between those 2 points, but that's not the quickest way to the beach. Some are a lot shorter. And so this is where perpendicularity comes into play, because not only is the shortest distance between a point and a line some segment, it's going to be a perpendicular segment. And we can kind of see that illustrated here. If I were to draw a segment connecting A and P and B and P and C and P, one of those three is much shorter than the other two. Namely, hopefully you'd realize that B and P is much shorter segment than, say, connecting A and P or C and P. And what that's illustrating is that I can even go shorter than this segment. It's the shortest of the three possibilities, but if I were to get even more perpendicular, and hopefully you understand that this is a horizontal line, so perpendicular to that should be a vertical line. So if I were to make a point right here, that would be an even shorter distance than B to P. Okay, and in fact, what I would find is that as I, say, measure, if I wanted to measure from P to C and I get some length, and then from B to P, and hopefully you realize that that's much shorter than C to P. But if I were to continue to rotate this to find the shortest distance, I would find the shortest distance there. And then if I kept rotating away, it would start to lengthen again. Okay, so as I swing back and forth with that measurement, the shortest is actually at its perpendicular point. And so that's going to be the important thing to function with here. The main examples that you're going to see in this section and in the next section, in section 5, or final section for this chapter, the main questions that you're going to see is you're going to be given some point or some location and asked to find the distance, the shortest distance to that finish line, that segment, whatever it might be. And the fundamental thing to work with is that we're going to want to find the perpendicular segment that connects the two. Because again, maybe you're trying to get to the beach and you want to do it in the quickest way possible. And you have all these cities to choose from. Well, the one that's closest to perpendicular will be the shortest distance. And maybe you have a time constraint, like maybe you want to do a quick turnaround trip in the day. You're not going to be able to do that going to a farther destination. You can get more time at the beach by going to something a lot shorter. So that's how it's kind of used in real life. And now something a little higher stakes, like say if I was, our location was say here just being Earth, and the surface I was trying to get to was, say, I don't know, the orbital path of another planet or moon, and I wanted to launch a rocket to get there. There are lots of ways I could connect with that pathway. Doing it in the shortest possible way will save me literally millions, if not billions of dollars in fuel, different kinds of adjustments that have to happen along the way. So again, this is used a lot in real life. And there are lots of other examples I could pull. All right, so one thing to also understand with this video, this is just going to be the first part of two. I'm going to focus mostly on properties in this one, and then the second video, I'm going to do one example dealing with something like this, finding the shortest distance between a point and a line. But for right now, let's jump into a couple of the other properties you're going to see in this section, and then in the second video, you'll see the example. So, different theorems that you're going to see in this section. Let's just talk through each of these. This will be pretty brief. The linear pair perpendicularity theorem. Okay, just so you recognize this again, anytime you see this symbol, this means perpendicular. It even looks a little bit like a segment and a line that would make a 90-degree angle. But linear pair perpendicular theorem. Just to remind you, linear pair means the pair means two things that make a line. Okay, so the fundamental thing to understand there is as soon as I have a line, I know I have a 180-degree measurement. This perpendicular thing, let's just jump right into it. Basically, if I see this situation, I have two things that are perpendicular to each other, two lines, and I have angle 1 is congruent to angle 2. That only happens if they both equal 90 degrees. This is basically a long, complicated way of saying that if I have a line intersecting another line so that the angles are congruent, there's only one combination of angles that can make that true. And that's if I have a 90-90. And the reason why that is because it makes a straight line. Okay, so the only way to split 180 degrees into two equal pieces is if I get 90-90. So that would force both of these to be 90-degree angles. All right, second one, perpendicular transversal theorem. So the transversal term comes again from our last couple sections. Basically, I have two lines crossed by a transversal. So line J right here would be called our transversal. And this basically says if I have two parallel lines, so this is actually similar to section 2. I start with parallel lines. I see that with my red arrows. And my transversal intersects those two lines, crosses the H, in a way so that it makes a perpendicular 90-degree angle. So I start with this scenario, two parallel lines cut by a transversal, so that makes 90 degrees on one line, then it also has to be the same on the other one. The reason why this is true is actually from section 2. If I use corresponding angles, then this top left one is 90. This top left one must also be 90. So basically 90, 90, they're both perpendicular to each other. Okay. So if I have two parallel lines crossed by a transversal, so that makes 90 degrees, both of the intersections have to be 90 degrees. Consequently, if I were to analyze each of these other angles, I would end up with 4 90-degree angles here and 4 90-degree angles here. All right, our last one, lines perpendicular to a transversal. This is kind of the flip side of that coin. So this is more like section 3, where now I'm starting with, say, corresponding angles. Say top right, top right. And so here's our situation. If M and P are perpendicular to each other, so I have a 90-degree angle, and that same line P, that same transversal, is also perpendicular to some other line. So this is like section 3. I have corresponding angles starting that are congruent to each other. They're the same. They just happen to be 90 degrees in this case. So this is a very specific version of that. Then these two lines have to be parallel to each other. Why? This is in section 3. Section 3 said basically if I have corresponding angles that are congruent, then the lines that are crossed by that transversal have to be parallel to each other. All right, so these are the theorems that you will see throughout the section. They'll be pretty easily identified. They'll look similar to these situations, just the diagrams themselves. So just be aware of those working forward. And in the second video, I'll deal with our one example from this section. All right, good luck.